Hey everybody, in this video we're going to talk about the differential rate law, and we're going to talk about some of the math and how to determine what the rate law is, and then we're going to solve some sample problems just so everybody understands. Okay, so once we get through kind of the beginning of all of the kinetics, we have to get into some of the math. Okay, and so in this case, the math here is that the rate law, R, equals K times the concentration of M raised to the M power, so it's the concentration of B raised to the N power. Okay, and so now R is the rate law, or is the rate. This tells us how fast the reaction is going. Okay, it's in moles per liter time. Let me make sure that I write this so that you see what's going on here. Moles per liter, and then whatever your time unit is. And when I write time, I write it T with a dingus. Okay, I call it a dingus. It's not really dingus. It's called a terminal. I had to double check I knew what that was. Anyways, and so that way it's not confused when you're writing a plus sign or if you have like a capital T or whatever. Okay, so the rate, the rate is equal to some concentration of the reactants. Okay, so this would be reactant, this would be a reactant. Okay, and so it's equal to the concentration of the reactant raised to some power. Okay, and so the rate is equal to the concentrations of the reactants in molarity raised to the power of M and N, and that's called the order of the reaction. Okay, now I would suggest that you kind of write this stuff down, and then we'll talk about it, and it'll make sense kind of at the end when we go through the sample problem. That way you can see it all in action. Okay, and then there's this thing that's called K. Okay, K, lowercase k, is what we call the rate constant. And the rate constant is not going to change unless the temperature changes. But I do want to make a little bit of a teaching note about K. When you write it, try to avoid writing a K that looks like a capital K. Capital K is the equilibrium constant, so you want to write it so that I know that it's a lowercase k. So when I write it, I was kind of taught to write it as a cursive K, script K. That way it looks different than if I was doing an equilibrium constant, and you wouldn't have to guess which one is which. Okay, so just so you know, you'll see me write this. As long as I can tell the difference, then it's fine, but I just wanted you to know that it's very common to see these kind of switched, interchanged. So this is the general form of the rate law. This is what we call the differential rate law, or if you're a calculus buff, it's the derivative of the rate. Okay, and so this gives us that the rate is equal to this. Okay, and we are going to find out what these things equal the order. Okay, now before we find out what they equal, let's talk about what the order of a reaction is. Okay, the order, really what the order does is it shows how the concentration will affect the rate. In one of the previous videos, I talk about collision theory. Well, as we increase the concentration, typically the rate of the reaction, how fast the reaction occurs, will speed up. And so that order will tell you how much it will change. Okay, and so I will tell you, for the most part, this is going to be a whole number. It's very rarely determined to be a decimal. Okay, very rarely do we get that. So it's probably almost always going to be 1, 2, 3, 4, some sort of positive whole number. It could be 0. It could be, sometimes it could be a half, but more than likely it's going to be some sort of positive whole number. Okay? So, and then I guess we could chemically talk about why that is. Typically it's a whole number because as we increase the concentration, now we're getting more collisions. So if we have more collisions, we know that we are going to increase the speed of the reaction. More collisions typically mean an increase in the speed of the reaction, increase in the rate. So that's why, you know, as we increase the concentration, that power is typically a whole number positive thing. Okay? Okay, and there are two different types of orders in the problem. If we look at the general rate law, okay, there's the individual order, okay, and that would be this power that is immediately following A, and that's the order, we would call that the order of A. And then this one, I'll put it in a different color here, the one in black is the order of B. Okay, and so those are the individual orders of the reaction. And then you can find the overall order. The overall order is M plus N. It's just these two powers added together. Okay, and that's really what the orders are. Okay, now usually in order to determine the orders of the reaction, we have to do this experimentally. And you are going to see this 9 times out of 10, maybe even more than that, done using the method of initial rates. Okay? And I kind of explain this here, what the method of initial rates is, but I think the more powerful thing is actually going through sample problems so you know how we do it in a sample. Okay? And so we'll do the sample in the next slide, but lastly, before we do the sample, let's talk about the rate constant. Okay, and so the rate constant is just a proportionality constant that tells us how the rate is proportionally equal to the concentrations raised to the power that they are given. Okay, and so we can usually determine this using the method of initial rates again, and we have to find the orders before we find the rate constant. Okay, so it kind of gives you like a stepwise thing to do. Okay, method of initial rates, find the orders of the reaction, then find the rate constant. Okay, so let's take a look at this sample problem. Okay, now you can pause it and you can look, you can copy down the question. Let me pull out my calculator. Okay, so let's determine the order of this reaction with respect to NO, with respect to Cl2, and then we'll determine the overall order of the reaction. Now, let's bring up this guy, and then I'm going to show you some of the chemistry relationships, and it will be cool. So, let me interpret the data for you a little bit. Okay, so what we are doing is we're doing one experiment, or we're doing the same reaction 4 different times. Okay, that's kind of what we're looking at here. Okay, so in the first reaction here, we started this with this and this concentration, and then we measured the rate. We measured the rate of the reaction to be this. Okay, and then we did the reaction again, and what we did is we changed the concentration of one of the things to get a new rate. And so what we do in order to do the method of initial rates is we determine, we do several different experiments, and then we do 1, 2, 3, 4. So in this case we did 4 experiments, And for each experiment, we change the concentration so that we can see how changing the concentration is going to affect the rate. Okay, so let me show you a little bit of the chemistry. Here, what did we do to the concentration? NO, okay, and what did it happen? We doubled it. Okay, we doubled the concentration going from experiment 1 to experiment 2. Did we do anything to this experiment? No, this stays the same. So why did the rate change going from here to here? Well, the rate changed because we changed this concentration. If this concentration didn't change, then the only reason why the rate changed was because this concentration changed. So what about this? How did this change? Well, the rate changed by 4 times. So by doubling the concentration of NO, what we're doing is we're quadrupling the rate. That's the relationship here, okay? So that means that that is a second order reaction, okay? So what we know is that NO is a second order reaction. The concentration of NO is to the second power because 2 squared is 4, okay? Now if we do the same sort of thing with a, instead of with NO, but with but now we're going to hold the NO constant. So from here to here, let's see. So now going from here to here, now NO is held constant. So going from looking what happens experiment 1 to 3, what happens to these two? Well, we doubled the concentration of Cl, and what happened to the rate when we doubled the rate? When we doubled the concentration, well, that rate doubled. So if it's a direct linear relationship, that means the order of the reaction is to the first, because 2 to the first equals 2. Now, the overall order then is going to be 2 plus 1 is going to be 3. Okay? But now what I want to do is I want to show you the math behind this, because the math is kind of an interesting and can help us solve these problems fairly straightforwardly. Okay, so let's go here. Let's go here. Okay, I'm going to close one of these, and then I'm going to open the other. Okay, so here's what we do in order to determine the order of a reaction, okay, or the order of the order of one of the things. Okay, so I'm going to go and I'm going to pull up this slide so I can easily go in between the two here. Okay, that probably all looks familiar to you. Okay, so this one. Okay, so here, what we have is we have a reaction. We've done it 4 times. So what we're going to do is we're going to compare the experiments. So we're going to compare the rate of experiment 2 to the rate of experiment 1. Why did I do it that way? Because I wanted to pick the one that is bigger, so it goes on top. Okay, see, it should go on top. So I picked experiment 2 to go first. And then that means the bigger number will always go on top. Okay, you can do it either way, but that's fine. Okay, so we're going to compare R2 to R1. Now, what's the general form of the rate law? Is K times the concentration of, now we're going to use, instead of A, we're going to use the concentration of the reactants, NO and Cl2. So it's the concentration of NO raised to some power M times the concentration of Cl2 raised to some power N. And so that's the rate law for experiment 2. Now the rate law for experiment 1 is the same thing. NO concentration of NO raised to the M, concentration of Cl2 raised to the N. So now mathematically, this is why we can do this to figure out what the powers are. Okay, and I'll do this in a different color here. So we'll do it in green. What happens? Well, when you compare rate 2 to rate 1, K, the equilibrium constant, the rate constant is the same for every reaction. As long as it's the same reaction at the same temperature, the rate constant is the same. Okay, and now also comparing experiment 1 to experiment 2, the concentration of Cl2 is also the same. So that also will cross off. So now what we get is a simplified version of the rate law, where we get R2 over R1 equals the concentration of NO to the M over the concentration of NO to the M. Okay, so now this is the math. Okay, well, what's R2 and R1? So this is 5.72 times 10 to the minus, 6 times 10 to the minus 6 over 1.43 times 10 to the minus 6. That's rate from experiment 1 equals, and now we want the concentrations, 0.5 and 0.25 equals 0.5 for experiment 2 over 0.25. And mathematically, if both the numerator and the denominator are raised to the same power, we can raise the whole thing to that power. Okay? And so now we just math it. Okay? So what is this? 4 equals 2 to the M. So that means that M equals 2. And that's what we determined earlier. Okay? So now how do we do the other one? Well, again, we're going to pick two. We're going to do the same thing where we pick the, instead of where Cl2 is being held constant, we're picking where NO is being held constant. So we can pick either 1 and 3 or 2 and 4. So we're going to pick 1 and 3. Let me tell you that it will work out the same no matter what. Okay? And then we'll pick 1 and we pick 1 and 3 to figure out what the order of Cl2 is. Okay, and then so now we plug that in. So to find the order for Cl2, we get Cl2. So again, I'm going to write it out completely. We're going to do R3 compared to R1. And that's going to equal K times the concentration of NO. But now we have the power. We have the order. So that's 2 Cl raised to the N. Now that's the one we're trying to solve for. And again, the rate law for R1, I guess that's Cl2 raised to the N. Okay, so now same thing as last time. The K's cancel out because they're always the same. They reduce to 1. And again, this does too because those concentrations are held the same. So now we get the R3, which was 2.86 times 10 to the minus 6, over R1, 1.43 times 10 to the minus 6, equals, let's see, the concentration of Cl2, for that one was 0.5, over 0.25 raised to the N. And so now at this point we math it. Okay, 2 equals 2 to the N equals 1. Okay, and so now what I'm going to do is I'm going to take this one step further. Okay, and I didn't even need my calculator at this point. Okay, I'm going to take this one step further. Okay, the question just says, what is the overall order of the reaction? Okay, the overall order of the reaction is 3, because you take each individual order and add them together. So M equals 2, N equals 1. So the total overall order is 3. Okay, but now I'm going to take it one step further. I'm going to determine K. Okay, the equilibrium, or see, I keep saying equilibrium constant. I'm going to determine the rate constant. So now, in order to determine the rate constant, I can pick any one of these experiments. Okay, I'm going to just choose experiment 1 just because it happens to be the one that's right there. Okay, so if I'm going to determine K, now I use the rate equation. R equals K, concentration of NO, what was the power? 2, concentration of Cl2 raised to the first. Now I am always going to write a to the first there because I want everybody to know that I calculated it and it came out to be 1. Okay, so now the rate in experiment 1 was 1.43 times 10 to the minus 6 equals K, which is what we're solving for, times the concentration. The concentration was let me just double check, 0.25. Each of them were 0.25. So it's 0.25, but that's squared, times 0.25 to the first. Okay, so now we just have to solve for K. So 0.25 squared times 0.25, okay, and then 1.43 times 10 to the negative 6, make sure we, times 10 to the negative 6, divided by that answer. So we get K equal to 9.15 times 10 to the minus 5. Okay? And so that's your equilibrium constant. Not rate constant. Okay? So that's how you use the method of initial rates to determine the orders of the reaction and the rate constant.